Okay, so last time we asked a question, didn't get around to answering it, right? So the question was a little bit of a thing to state, of all possible directions that I might move from a given point in the domain, which direction is the direction that makes our directional derivative, namely, how fast is the function increasing? How steep is it as I move in the domain in that direction? However you want to interpret it. What will make this as big as possible? So how do we maximize that directional derivative? In other words, what's the direction of fastest increase or the direction of steepest ascent? However you want to phrase that. So we have these two different phrasings of the question. Again, direction of fastest increase, direction of steepest ascent, and they're at different phrasings of the same thing. Again, I have a slight preference for this one because it doesn't depend on your ability to view the situation as a graph. Right? You don't have to view it as a graph. Okay, so now let's get around to answering the question. We want to make our directional derivative as big as possible, and conveniently, we have a formula for our directional derivative. Here's our formula for how to compute directional derivatives. Right? Dot product with the gradient. This is what I want to maximize. Here's how we compute dot products. Right? Product of the magnitudes times the cosine of the angle. That being, again, the angle between the two vectors. Don't forget, by assumption, we're only considering unit vectors for v, because that's how directional derivatives work, right? And that means that this magnitude of v is 1. Definitely 1. And a factor of 1 we can just throw away. Okay. So altogether then, this is the expression that we want to maximize. But we can actually hone this down a little bit more, because keep in mind we're entertaining all possible unit vector directions from which I might move, but I haven't actually moved at all. I'm just contemplating possible directions of motion. So let's ask the question, what can I say about the gradient here, the magnitude of the gradient? Well, I'm still at this same point. I haven't moved yet, so the gradient is not changing, right? Given as I contemplate all these different green directions, the point A is still the point A. And the gradient at that point is not changing, and so the magnitude of that gradient constant. So this factor constant. So all of a sudden, this question's gotten much streamlined. You want to make this directional derivative as big as possible. Really all we need to do is figure out how to make cosine theta as big as possible. And that's an easy trig question. Cosine theta is as big as possible when it's equal to 1. Which happens when theta is equal to 0. And don't forget theta is this angle here. So I need for that angle, I need the angle between the gradient and the direction that I'm going to start moving. I need for that angle to be 0. Or said differently, I need to actually move in the direction of the gradient itself. That's the ideal direction. What do you think? Everybody okay with that argument? A little trig argument, basically. So, natural question. What's the direction of fastest increase? Obviously natural question, and simple answer. Go in the same direction that the gradient is pointing. Okay, now the natural next question to ask is, okay, so this is the way, this is the direction to go to increase the function as fast as possible. How fast is the function increasing as I move in that direction? In other words, what is the value of this directional derivative? Going in that optimal direction, of course. Well, as I go in that optimal direction, I want to compute that directional derivative. We have a formula for directional derivatives. Again, same formula we had above. Don't forget, V is gradient divided by its own magnitude. Notice that gradient dot gradient is magnitude squared. And, of course, magnitude squared divided by magnitude is magnitude. And so we have a nice crisp answer to this second question as well. What's the direction of fastest increase? The direction of the gradient. How fast is the function changing in that direction? The magnitude of the gradient. Weirdly, the gradient kind of is the answer to both of these questions. To the direction question, the direction of the gradient. To the magnitude question, the magnitude of the gradient. So I like to rephrase this whole discussion not as, here's a couple of questions, what are their answers, but rather instead view this as what I like to call a geometric characterization of the gradient itself. And so let me remind you, what is the gradient? What have we been doing with the gradient so far? The gradient has been a notational convenience. It's a shorthand for writing down all the partial derivatives. It's been an algebraic tool. It's the thing that you dot with to compute certain things. It's been an entirely algebraic object. And now we have a way to think of it geometrically. Specifically, its two defining geometric features, its direction and its magnitude, I can describe directly now. The direction that the gradient points is the direction of fastest increase, and the magnitude of the gradient is what is that maximum slope, or how steep is it in that direction, or however you want to say that. Okay. So, geometric characterization of the gradient. Is everybody on board with this? All right. Okay. So let's see an example. We've got a hill. The hill is in the shape of this graph. So a graph of that function. Keep in mind, graph means z equals whatever the function is. So we have z equals f of x comma y. That's the graph. And we find ourselves at this point, and as we stand on the hill at that point, we want to know which direction is uphill and how steep is the mountain. How steep is the hill at that point? Okay, is everybody on board with the question? And before I get into answering it, I want to address a terminological sloppiness that is actually very convenient, and I'm for it. I'm not criticizing. Nevertheless, it is a little sloppy, but we do need to recognize what the sloppiness is here. That's where we are. That's where we're standing on the hill, right? But if you're standing anywhere on the surface of the earth, how do you describe your location? Like if I'm in Durham right now, right? How would I describe my location? I guess I could look it up on Google Maps, and I would call my friend so-and-so and say, hey, I'm at the following latitude and longitude. I would give X and Y coordinates. I wouldn't say I'm at the following latitude and longitude and altitude. Well, my friend's going to assume I'm on the surface of the earth, right? If I were at the bottom of a 300-foot deep mine, I'd probably go ahead and mention that, right? But if I'm on the surface of the earth, yeah, of course I'm on the surface of the earth. That's understood. It's a given, right? So even though technically we are at this point right here on the hill, we're at the point sitting above 1, 3 in the XY plane. That's pretty awkward language, and most of the time people would just say, yeah, I'm at 1, 3. I'm at the following longitude and latitude. It's a pretty convenient sloppiness, and it's a very common way of talking. So now I deliberately went to the trouble of saying the awkward language of I'm at the point sitting above 1, 3. Going forward, I probably won't do that. And it's going to be part of the proper interpretation of a question is to realize that when I say I'm at 1, 3, well, of course I'm not, buried 50 feet underground. Right? I'm on the graph, of course. Does that make sense? Is everybody happy with that? Okay. All right. So we're going to conflate these 2 points. These 2 points, we're going to kind of treat them as if they're the same and interpret accordingly. Okay, so now let's answer the question, which way is uphill? Which way is the direction of fastest increase? Well, it's the direction of the gradient vector. And I can compute the gradient. I can plug in the point in question. By the way, when I say plug in, I mean plug in for x and y, which are 1, 3, which are technically not the point that I'm at. I'm actually on the hill. I'm at an x, y, z, but it's only x and y that I need to talk about because that's the point where gradients are evaluated, right? So 1, 3 gets plugged into here, and that gives me this. Let's do it like this. That gives me this as my gradient. Everybody good? All right. How steep is the hill at this point? Well, again, when I say at this point, from a computational point of view, I'm at this point. From a reality point of view, I'm actually at that point. But of course, computationally is all that we really need to worry about here. So we plug in this point into gradient. Well, we already did. We already plugged in that point into the gradient, and the magnitude is telling us how steep it is, and that magnitude easily computed from that vector to root 2. So it's pretty steep at that point on the hill. That's, 2.8 something, right? That's pretty steep. That's about like this. Steep hill. Okay. All right. Everybody happy? Yes. Oh, yeah, sure, fair. Typically, when you, think about the XY, axis system, right, we typically think of, Y as being north, and x as being east, right? And so with that point of view in mind, well, there's the positive direction of y right there. So this is north, and if that's north, then this direction here is southwest. Does that make sense? Just map coordinates, yeah.
And what units would you say like the gradient are? It's like 2 root 2 pretty steep, but 2 root 2 what?
Yeah, well, that's a good. I don't know if there is a name for the. In some sense, there are no units because a steepness is a slope, which is a ratio of two things. And if you measure the rise in feet and you measure the run in feet, the units cancel. So a steepness of 1 is always 45 degrees, and it doesn't matter if you're doing metric or English or whatever. It's always just a proportion. Is that cool? Yeah. All right. Good stuff. Okay, so moving along, we're going to talk now about level sets a little bit, calculus of level sets. We know very little so far about the calculus of level sets. So let's consider a level set called S. It's the set of points where f is equal to whatever our function f is, equal to some fixed constant. Every point on this surface, f is always equal to the same value, c. Okay. And so let me ask the rhetorical question, what's the value of f then at this point on the surface? Well, it's on the surface. So the value of f is c. Okay. Now, related question. If I were moving along this curve here inside of the surface. So imagine an ant, right, crawling along this surface. And he, momentarily is at the point in question, and then he continues crawling along the surface over to here. What's the value of f at any point on that curve? Well, it's on the surface, and so c. It's every point on this whole surface. The value of the function f is always c. So I can ask then the related question, at the moment that the ant is at that point, and at that moment he's moving with that velocity, whatever that direction tangent vector is. Well, if the function is constant as the ant crawls along this curve, and if as he crawls along this curve he's moving with that velocity, then I'm just going to kind of piece those together. As he's moving with this velocity, he's staying on this curve, and staying on this curve means the function is constant. And so as he's moving in that direction, the function is not changing. Its derivative as he moves in that direction is 0. Because it's constant. Is everybody happy with that? Okay. All right. Now the thing is, why that vector? That vector there, let me get into the highlighter mode here. So that vector, well, the pencil's really better. Okay, so as he's moving in that direction, the dfds is 0. But that was just some arbitrary tangent vector. I could make the same statement about that tangent vector or this tangent vector or what have you, any tangent vector. In fact, any vector parallel to this tangent plane, right? This is an entire plane of tangent vectors, which, as an ant moves in one of those directions, I remain on the surface where the function is constant, and the function, therefore, not changing in this derivative is always 0. Okay, so what this buys us is, if you think about it, dfds is one of our interpretations of the directional derivative. The directional derivative is computed with a dot product. So if I say that the directional derivative, if I say that dfds is 0, I'm really also saying that this dot product is 0. And that means actually a tremendous amount. This says that for every tangent vector, every single tangent vector, let me highlight this in blue. For every tangent vector, the gradient's perpendicular to it. The gradient's perpendicular to every tangent vector. This whole, at this point, this entire plane of tangent vectors, the gradient's perpendicular to all of them. And there's really only one way that could be the case. If the gradient is perpendicular to all of these tangent vectors, then the gradient would have to be perpendicular to the entire tangent plane, which you might find convenient to rephrase as the gradient has to be perpendicular to the surface itself. Yep.
Just to make sure I understand, the dfds is equal to 0, and that's a level set?
Yes.
So within each plane of the level set, the function isn't changed?
Within each level set. Yeah, so so a level set refers to just a single level set, and there are other level sets elsewhere that we're not talking about. I'm just talking about one given level set. And yeah, that's right. Wherever you are on that level set, the gradient of f has to be perpendicular to the level set itself. Yeah, yes?
If f doesn't change, then why intuitively would it be pointing like that?
Well, f doesn't change as you move in these directions. Right, but f absolutely changes as you move, in this direction, right? But when we're talking about these tangent vectors, these tangent vectors are what we're restricted to if we're talking about moving literally along the level set itself, right? So moving in a different direction that's not a tangent direction, well, different story. Yeah. Okay, so this is the really nice fact. Gradients are always perpendicular to level sets. But, of the same function. So if you're talking about a gradient of f, that's going to be perpendicular to level sets of that same f. Okay. So I want to show you a use of this. Oh, before I go on, real quick, an interpretation that you could make of this. This is a great example of what I've previously referred to as the calculus of level sets. Right? So we talked about the calculus of graphs and certain statements that you can make about partial derivatives and slopes of tangent lines, the cross sections in certain directions and all that. That's all in the context of if the picture you're looking at is a graph. So that's all calculus of graphs. This is a great example of calculus of level sets because the picture that we're looking at, the picture where I make the geometric statement, hey, perpendicular, this is perpendicular to that. The picture in question is a level set picture, not a graph picture. So calculus, these are gradients. Gradients are made up of partial derivatives. That's a derivative. That's calculus. And level sets, because that's the picture in question. So this is like I say, a great example of the calculus of level sets. Okay, how we're going to use that. I'm going to revisit an old question, that of how to find a tangent plane. We already know an answer to this, specifically if you're looking at a graph. Now, again, maybe you are. Right. If you're looking at a graph with some surface, and you're interested in this tangent plane at a given point. And again, sloppiness of language. Okay, when I say at this point, well, the point itself might be up here on the graph, but that's sitting above a point in the domain AB that are the values I'm actually plugging into the function, right? What you plug into f is just x and y. So you could say we're looking at the point A comma B. That'd be a convenient, albeit a little bit sloppy, but a very convenient and understandable way to describe what we're at. Where we actually are, of course, and just to be explicit about it, we are actually at a point on the graph which is in space, which has 3 coordinates, the first 2 of which are x and y. These x and y coordinates right there. Right? And the third one of which, of course, is the value of the function. So again, we're going to be a little sloppy in language. You could be talking about the tangent plane at this point, and you might say the tangent plane at A comma B, and it's understood that you mean above A comma B. Okay. All right. So all of that noted. We were looking at a graph, and again, this surface being a graph of f, this is what graph means, z equals. And then don't forget, we've got this little algebraic fast one we can pull. We can take an equation like this, and we can just kind of, move one term over to the other side of the equation, and this is morally the same equation, right? Certainly it's an equivalent equation, But having written it like this, I can take a different point of view on this. Now I can view this as being a level set. It's not a graph. It's a level set of a different function. It's a level set of this new function g. Right? Certainly not the same function as f. But it remains, I'm looking at a level set now. And so phooey on thinking about this as a graph. I want to completely reinterpret this as this surface is a level set. And so the question of finding this tangent plane, well, now I'm trying to find a tangent plane to a level set, specifically a level set of this function here. And how do we find equations of planes? Well, to find an equation of a plane, I need to know a normal vector. So I need to know a vector. Just for aesthetics, let me draw this at the point there. I need to find a vector perpendicular to this tangent plane. Well, that would mean that this vector is perpendicular to this surface, which would mean that this vector that I'm looking for needs to be perpendicular to a level set. Where have we heard that phrase before? A vector perpendicular to level sets. Well, here you go. The gradient is perpendicular to level sets. So this particular fact of, again, what I like to call the calculus of level sets is exactly what we need here. I can choose for this vector to use as my normal vector in here. I can just use the gradient. Specifically the gradient of this function g, right? Now definitely not f. Gradient of f is not even the right dimension. Gradient of f only has 2 coordinates. This is clearly a 3-dimensional vector. Gradient of f does not do what I need it to do. But the gradient of g, perpendicular to the plane in question, serves as my normal vector, and we're in business. Everybody happy with that? Yeah.
And if you use the gradient of normal vector, things that the function not changing.
Yeah, well, because of this conclusion right here that gradients are always perpendicular to level sets. which is exactly what we needed, right? I mean, that's if you're trying to find an equation of a plane, you need something that's perpendicular to that plane. Are you happy? Yeah. Okay. All right. Okay, so it's all over but the algebra. So we do need to take the gradient. How am I going to take the gradient of this function here? That function, well, I need to take the x partial and the y partial. Well, there's a minus sign to be thought about, but other than this minus sign, the x and y partials of g are just the x and y partials of f. Yeah, question. No, I'm saying the gradient of g is perpendicular to level sets of g. And as we previously viewed, this surface right here, I can view as being a level set of that function g. So gradients are perpendicular to level sets. Is that cool? Yeah. You have to be careful. It's tempting to like I think if I heard you say correctly, I think I heard you say gradient is it perpendicular to the function, right? But that's a mismatch of type, right? So perpendicularity is a geometric statement. A function is not a geometric thing. So you need to know, we talked about the graph of the function or the level sets of the function or what have you, and in this case, level sets. Yeah. All right. Okay, and then lastly, the z partial. Well, there's only one z in this expression, and it's that one term. The partial of z with respect to z is just 1. Okay. So, yeah, it's really all over but the shouting at this point. We've got a normal vector. Here's the equation of a plane. N dot x minus x naught is 0. So, there it is. X minus x naught is this business right here. And don't forget the point x naught we already talked about. That point x naught is this right there. And you multiply this whole thing out and move terms around, etc. And again, it's just algebra. By the way, it's a healthy exercise. Make sure that you're good with this. Make sure you can do that. But multiplying it out and collecting terms. And notice I've solved for z specifically here in that rearrangement. Notice we get a familiar result that the tangent plane is the graph of this formula, which you recognize as being the linear approximation. So, again, we already knew this result. This is not a new result. What it is a new approach. It's a new argument for deriving that familiar result. Okay, quick example. Now, I could just plug into the equation on the previous page, but just to elaborate on the argument, right? And the argument being the object of interest here. If you're asked to find a tangent plane to a graph of a function, you can use the same trick we just got through using. Here's the graph that I've been asked to find a tangent plane to. Let me do some trivial little algebra here. Again, just moving terms around, right? And as a result of moving terms around, I'm going to reinterpret this graph as being a level set of a new function. And my new function is this thing here. Everybody with me? Once I've got it viewed as being a level set, I don't really care about the whole graph business anymore. Once I view it as a level set, then, well, let's see here. The gradient of that function, the function whose level set I'm looking at, that gradient is going to be my normal vector. And I can plug in the point in question and get that value. That's my normal vector, and arithmetic and victory. Everybody see the argument there? Yep.
So the tangent, but never.
Oh, okay. All right. Yep. Okay. All right. So moving along. So there's a new topic to talk about here. I am going to. This is another one of these topics that I wish we could spend more time on, but we can't. So I'm going to give you a quick and dirty point of view on how the implicit function theorem works. But I think it's appropriate to the course in the sense that I'm going to leave you with what I think is good intuition for what's really going on, and we're going to be extremely non-rigorous about this. But that's where we are. So here's the situation. You might have an equation in two variables. For example, this curve here. Keep in mind, whenever you have an equation, however many variables you have, you can always kind of move all the terms over to the left. Any equation you have, you can rewrite as something equals 0. So let's go ahead and do that. And the question I want to ask, awkward question, can I view y as being a function of x at points on this curve? And this is a hard question. We're going to get different answers at different points. And so let's start off with this point right here. Is y a function of x? Well, let me modify the question more appropriately. What do I mean by locally? Is y a local function of x, or locally can I view y as being a function of x? What we mean by locally is just look kind of in the vicinity nearby. Said differently, feel free to throw away as much of the rest of the curve as you want. Just chop it and throw it in the garbage can, not at all what we're interested in talking about. And so with this local modification in mind, the curve that actually remains after I've thrown a bunch away, it's just this little piece of blue curve right there. And that little piece of blue curve, does that pass the vertical line test? Yeah, it passes the vertical line test, no problem. So fine. So locally, yes, I can view y as a function of x. Is everybody good? Now, algebraically, can I solve for y? Oh, I have no idea. That's a separate question. That's not what we're talking about. I just want to know, is there any hope for being able to view y locally as a function of x? All right, now let's do the same thing at this point here. Looking at that point, is y a function of x? Don't make the mistake of saying, oh, hey, look, we're failing the vertical line test. Look, we hit that vertical line 3 times. Again, not what we're asking, right? We are asking the question of, at this point, locally. So, look only nearby. Look as myopically nearby as you want. Right? You can make this as small as you want. And looking then only at that little piece of curve. So now, again, this little piece of curve right here. Does that curve, ignoring all of this up here, this is gone, that's in the trash can now, all of this over here, gone, trash can. Looking only at this green little piece of curve, do we pass the vertical line test? Why, yes, we do. No problem. Everybody on board? See what I mean? Okay. All right. Here's where the problem is. So what I want to worry about for the purposes of the implicit function theorem, what does the implicit function theorem address? It addresses problems like this point. This being the sort of the vertical point there on the curve, if you will. That point, even if you restrict your attention locally, right? I've restricted my attention locally. Now let's look just at this little local piece of curve there. On that little piece of curve in green right there, we fail the vertical line test. That vertical line hits twice. Everybody see what I mean? And you could argue, well, that's, because you made your yellow circle too big. Make that circle smaller and smaller and smaller to get away from where these 2 points are a problem. Well, sure, but then there's going to be 2 other points closer on the curve. And no matter how small you make it, there's no getting around the fact that the curve is wrapping under itself there. And however little of the curve you look at, there's going to be, the curve has wrapped under itself. And you just, not even locally, can you view y as being a function of x. Everybody see the problem? Okay, so what we want to figure out then is how do we distinguish bad scenarios like this one from good scenarios like these. Okay. Now, before I give you the answer to that question, let me ask and answer the related question of who cares? So here's the problem. As much as I don't want to worry about the rigor of this situation, I do want to make sure that we don't inadvertently write down meaningless garbage. That's a problem, and you got to make sure that when you write stuff down, if you're claiming to be doing mathematical reasoning, then you got to make sure that the things that you write down actually mean something, as opposed to just being meaningless collections of words that don't fit together and make any sense, right? So here's the issue. If I'm at a point like this, and if I say dy dx, I can make sense out of what I meant by dy dx at that point. It means, all right, I'm just going to look at this little nearby piece of curve. I don't need to worry about what's going on over there to make sense out of a tangent line at that point. And locally, I can view y as being a function of x. And when I have a function, I can talk about its derivative. Okay, so dy dx makes sense at that point because y is locally a function, and you take derivatives of functions. The problem then, though, if I'm at this point, I can't even ask the question of what is dy dx. It's not that there isn't an answer to that question. It's that dy dx itself doesn't make sense because y isn't even a function in the first place. Even locally, right? Even restricting my attention to just nearby, y is not a function. You can't take a derivative of something that's not a function. Derivatives apply to specifically and strictly functions. You can't take a derivative here of y any more than you could take a derivative take a derivative of a point. It's not take a derivative of a surface. That's not a thing, right? That doesn't make any sense. You can't take a derivative of bicycle to take it to an extreme silly point. So I need to know under what circumstances I can view y as a function of x, just so I can talk about dy dx, much less compute what it actually is. Okay, so that's why we have to care about it. Here's how we answer the question, and this is where I get real sloppy and intuitive, and let's not worry about it. Here's what a problem point looks like, right? This is where y simply cannot be viewed as a function of x, not even locally. The problem is that the curve is at that moment, at that point, that's exactly where it wraps under itself. Is that cool? And it's the fact that the curve is wrapping under itself that's going to make it, no matter how close I get, I'm always going to have vertical line test failures because at that point, that's exactly the point where the curve is wrapping under where it had already been. Okay, so that's the what a problem looks like. Now I make the observation that if you have that problem, innocent observation, there's going to be a vertical tangent line, right? Because it's in the process of wrapping under itself, so it's got to be vertical at that point. And don't forget now that the curve itself is a level set, and gradients are always perpendicular to level sets, which means gradients are going to be perpendicular to the tangent line, and if the tangent line is vertical, that means that the gradient would have to be horizontal. Is that cool? Just a geometric appeal. Well, of course, if the gradient is horizontal, if you think about it, what does horizontal mean? I'm running out of colors, apparently. Horizontal means that the second component of the vector is 0. Well, the second component of the gradient is the y partial of f. Okay. So all together then, let's streamline this. If we have a problem, if this scenario happens where I cannot view y locally as being a function, then that will imply that this y partial is equal to 0. Why did I do that? Here we go. Okay, so bad news implies this is equal to 0. And now I remind you of the contrapositive construction. The contrapositive is where, you take your statement and you turn it around backwards and put not in front of both the hypothesis and the conclusion. So the contrapositive here, also true in other words, is that, look, as long as that y partial is not 0, then this whole story here can't happen, because in this above story, the y partial is 0. So if you already know that your y partial is not 0, nothing up here could happen. In other words, no problem. And you can view y locally as being a function. How are we doing? All right? Okay, so here's the three-dimensional version of the same thing. Now we've got 3 variables. 3 variables means that I'm looking at a surface like this. The equation of 3 variables is a surface. Again, I can ask kind of analogous question, can I view z as being a function? Well, golly, locally, of course, but it depends on which point am I looking at. So for example, at this point right here, up there kind of, if you will, near the top of the sheet of paper, let's see, like this, right? At a point like this right here, that point, just look nearby, forget about all this bit of surface down here, just nearby there, yeah, no problem, vertical line test, vertical lines will hit that neighborhood, each vertical line exactly once, and no problem. So at a point like this one, sure, you can view z as a function of x and y locally. So it makes sense to talk about things like the partial of z with respect to x in the vicinity of that point, no problem. But here's where things get bad. If you're at a point like that, where the surface is at the moment of wrapping under itself, you're going to have this same problem of, let's see here, because the surface is wrapping under itself, that means you're going to have a vertical tangent plane. And having a vertical tangent plane is going to mean that you're going to have a horizontal gradient vector. And keep in mind that a gradient vector is made up of a bunch of partial derivatives. Horizontal would mean that the third coordinate of that gradient would have to be 0. So, same argument that we made up here, just this is kind of the 2-dimensional version, this is the 3-dimensional version, and so we get the same conclusion that if this does not happen, if the partial with respect to z is not 0, then this is not our problem, right? This picture is not what's happening. Partial derivative not 0 means nothing's wrapping under anything, and you're good, it's fine, go ahead and view z as being a function. Okay. All right, here's the good news. Even though this picture is different from this picture, here we were trying to view y as a function, here we're trying to view z as a function. How do we keep track of what do I take a partial with respect to? Here's the good news. It's always whatever variable you want to view as being a function, you take the partial with respect to that variable. Whichever variable you want to view as being a function, take a partial with respect to that variable. And again, I'm not going to prove or generalize. I'm just going to kind of assert, notice the pattern in the examples we've seen, and I'm just going to state now the implicit function theorem. If you're looking at a level set, very importantly, level set. It's got to be a level set. If you want to view one of the variables as being a function, take the partial with respect to that variable. And if it's non-zero, then yes, you can. That's the deal. Now, always take a partial with respect to the variable that you want to view as being a function. Everybody on board? Yeah.
So far, we just talked about the case of which we're looking at a level set.
Yes, that's right, and it's very important to the whole setup. And it's got to be a level set. That's right. Yeah.
So for different functions, you have to make it a level set.
That's right. You got to if you're given some equation where you got a term over here and a couple terms over here, you got to move terms around, make it stuff equals constant. Absolutely, you got to do that first thing. Absolutely. Yeah. So in fact, let me go ahead and document that on the thing here as well. You're taking a partial with respect to the variable you want to view as a function. You're taking a partial derivative of the thing whose level set you're looking at. So got to be a level set. Okay, example. Here is a surface, and by the way, a pretty nasty surface at that. I don't know how I would draw this surface without a computer helping me out. I have no idea what this thing looks like. Kind of a bare. It's cubic, for one thing. Yikes. Okay. So, what are we going to do about that? The question being posed to me, can I view x locally as a function? Okay, so we want x to be a function, so I'm going to take a partial with respect to x. The thing I take a partial of is the function whose level set I'm looking at. So, this is the thing I'm looking at a level set of. So that's what I'm going to take a partial of. X is what I would like to, hopefully, fingers crossed, hopefully I would like to be able to view that locally as being a function if I take a partial with respect to x. And a little bit of algebra. This is what the partial ends up being. I'm interested in what's happening at this point, 1, 2, 3. So I've got to plug that point into there. And out comes 4. And keep in mind what the test is. The test is that partial derivative, at the point in question, is it not 0? Why, yes, indeed. Non-zero. And so, yes, indeed, I can view x locally as being a function of y and z. Is that cool? Okay. All right, now, next question. And again, part of the reason I want to be able to view x as being a function is so I can take its partial derivative. Let's say partial of x with respect to y. Now, given that I can't solve for x, right? Look at this. It's cubic in x. I can't solve for x. Forget it. It's not going to happen. How would I take a partial of x if I can't even solve for x? And there's a really nice answer to this question. By the way, we're going to assume that we've already established that yes, indeed, I can view it as a function. And with that being the case, take a look at this diagram here. This is what we're going to skip and not talk about because it's a little bit bulky and clunky, and there's a more streamlined, easier way to go about this. So I'm going to skip down to this diagram, which is telling us, it's a little bit sloppy. This violates one of my previously noted rules about diagrams and the chain rule, and it's okay in this circumstance. And don't worry about this part of it. You can take my word for it that this is fine. But notice we've got f as a function of a bunch of variables. F, though, remains constant. We're looking at a level set of f. Let's see here. We are choosing to view xi as being a function of the other variables. So, among other things, xi depends on xj. And now I'm going to ask the question, what happens if I start changing xj? Where do the changes in xj propagate? What are the paths along which these changes propagate? And here they go. If you change xj, well, that makes a direct contribution to how much f changes. But it also, if you change xj, that also causes xi to change, and xi, when you change xi, that also contributes to a change in f. Right? So this is all that happens. In some sense, when you change xj, that's going to directly contribute to a change in f, and it's also going to cause xi to change, and that's going to contribute to a change in f. But don't forget, both of these together, grand total, f, is not allowed to change. F is constant. So the actual total change in f has to be 0. Said differently, the amount of change that f gets along this path and the amount of change that f gets along this other path, they have to cancel because f is not allowed to change at all. Right? So these two things add up to 0, and we solve for what we're interested in, which is right there. And there's your handy-dandy formula. So yeah, make sure to know this formula. Real quick, I want to point out, don't forget this minus sign. That minus sign is essential. It's a very big deal. Without that minus sign, it makes it look like you think these things cancel, which of course they don't. These are not actually fractions. Right? That's an illusion. These are not fractions. You can't just cancel the partial f's. Right? So please, if you make sure that you don't forget that minus sign. This is the only evidence that you actually know implicit differentiation, as opposed to your thinking creatively, illegally about canceling things that don't cancel. So be very careful about that. We'll pick up here next time. Y'all have a good Wednesday. See you Friday.